Okay, so today and the next class will be about natural deduction. So we touched briefly about natural deduction last time, but was very minimum. So we will see a lot of natural deduction rules today, and as well as next class. Now these rules are in fact somewhat difficult for humans to learn, but it's very easy for machines to automate. So this is something that humans are now really competing with machines. It's very mechanical process. So once you see the rules, you can just write a program to generate such a proof. Okay? You have to be a bit clever, but it's not much demanding once you know how to write a code. Okay? On the other hand, for humans, we are often making mistakes when we apply these rules. Okay. So what is a natural deduction? So deduction is you can derive some conclusion from what was established before. So we have to start with something, although we can actually start with nothing too. But usually we have some thing called premises. So here phi 1 through phi n are something that are already known to be true. So you don't have to worry about how to prove this. So this is given truth. From these, you apply some rules, and these rules are the things that we are going to study today. You derive some new formulas called conclusion. Okay? So the rules tell us what formulas can be derived, and also it also tells us what formulas cannot be derived. Okay? So we are going to use this construct called sequence. So basically, if you have seen the homework 1, you see many problems about prove this sequence. So given these premises, you have to derive the conclusion. Okay? So there are some sequences that are actually correct, so you can actually prove in terms of natural deduction, and some are incorrect. So there is no way to derive these rules using natural deduction. So the first one is actually correct, second one is actually incorrect. That's what we saw before. So we talk about one pair of natural deduction rules, which is called conjunction. So there are two parts to introduce conjunction and also eliminate conjunction. Okay, and we saw this example before. So let me actually go over this example again. So what you do in natural deduction, you start with the premises. So you have to you can start with any premises. So P and Q are. Now, in general, you don't have to, of course, use all premises if you are enough to prove the conclusion with a limited set of premises that are fine. But usually for the homework problems or the textbook problems, you have to use probably all of the, most of the time you have to use all premises. So it's good to start with these premises. So we are going to write here why we write this. So these are the premises. Okay. Now our goal here is to derive the conclusion, and we don't know how many steps that we need to derive conclusion. So let me just write n here. Okay. Now in order to get to Q and R, you can think about the proof in two directions. So from forward, and from the beginning to the end, or end to the beginning. So to try to close the gap. So here the gap is between 2 and n, right? So we don't know how to fill this. Okay? Now, sometimes it's good to look at the goals and see what can be done. Sometimes it's good to look at the premises and what can be derived from there. So we are going to use both ways. For this particular problem, it's actually easy to look at the goal. The goal is Q and R, right? So in order to derive Q and R, you only need one rule, which is AND introduction, which means if you have Q and R already established, then you can derive Q and R. Okay? So here, the goal here is maybe, since I don't know whether this is true or false, let me just write Q here. Okay? Fortunately, R is already there. So if we can prove Q, I wrote in blue because I'm not sure whether this is okay to write here. I don't have the justification yet. Okay? But if I know Q is true, and also I know from line 2 R is true, I can derive Q and R. So this is conjunction introduction from, let's say, this is n minus 1 and 2. Are we together? We don't know just whether what is the justification for Q. That's why I left this part to be blank. Okay? But if we can somehow derive Q, then we can combine Q with R, so we can derive Q and R. Okay, so how do we derive Q? Luckily, at this point, it's easy to do. So now let's look at from the forward. Okay? So we already know P and Q is true, so we can actually derive Q to be true. How do we do that? Conjunction elimination. So conjunction elimination from line 1. In fact, there are two versions of conjunction elimination. The first version get the first formula. The second version get the second formula. So for this example, we are using the second version of conjunction elimination rule. Okay. Now, since this is actually valid thing, I can now write it as a red color. So all the red colors are proven to be true, right? And there is no gap in the proof. At this point, it's actually easy to, or actually it is good to look at from the beginning. So what did we say? Initially, we assume P and Q is true, and then we assume R is true. From the first premise, we derive Q. And then from the third line and the second line, we derive Q and R. So now n becomes here. Now we know that n is 4. Okay, so there. So this is the complete proof. Any question up to this part? Okay, good. So the other alternative notation that you sometimes see in the another textbook is a tree notation. So we can say premise. Premise is something that you can write in anywhere. So let me just write P and Q, and also another premise R. Okay. Now once we have this premise, these premises are actually above the line of the deduction rule. So from P and Q, I can derive Q, right? Because that's what happens with conjunction elimination, the version 2. Okay. Now once we have that, so just look at this pattern. So this part is exactly reflecting the pattern here, right? Okay, so this is where machines are good at. They're very fast at finding the pattern matching. Okay. Now once you do that, you derive now new formula Q, okay, and also the new formula R. Now if you know Q and R, you can derive Q conjunction with R, which is this rule. If you know Q is true, R is true, then you can derive Q and R is true. This is end introduction. So that's this one. I can write end introduction here. Okay? So this is another way to write the formula. Now, there are pros and cons of each approach. The first approach, you have to give a line number. Okay? So you have to pinpoint which line that you are using. Okay? In contrast, the tree notation is a bit easier because you don't have to worry about the line number. You just directly using you just directly use the deduction rules. Okay. And downside is, as I said before, if the proof becomes longer and longer, the tree becomes too large, so it doesn't fit to your page. Okay. While here, if you just write a lengthy proof, you just need to write down the line numbers. Okay, it's actually linear growth in terms of space. Okay, so in this class we are going to use the first notation a lot. But if you happen to worry about how these are working, you can try to look at the alternative way too. All right, and then we look at the double negation and implication elimination rule. So double negation is simply you can either add double negation or not. So if you have somehow proved this formula, not phi, you can prove phi, and vice versa. You can have phi and you can do not phi. Now you may say that, well, this first one seems to make sense. You want to derive some simpler formula from the complex one. But there are also some cases that you will see later when we apply these rules with other rules. Sometimes you want to make the formula more complex for the sake of some intermediate process. Okay. All right. And we talk about the implication elimination rule, which is also known as modus ponens, which is very intuitive, and this is something that you already know from your daily lives. If you know that P is true, and if you also know that P implies Q is true, then you can derive Q is true. Now, often mistake is if you don't have P, you only know P implies Q, and sometimes people say, well, the P implies Q here means that if it rained, the street is wet. This sentence itself doesn't say it rained or not, okay? And this sentence doesn't say that the street is wet. Something meaningful comes out only when P becomes true. Okay, if you don't know what is P, then P implies Q actually doesn't tell you anything. Okay, so this is common misconception that we have. Okay, what is a good example to use? Okay, so if I can't bite a dog, the dog will be dead. Okay? This sentence itself has no meaning. I didn't bite any dog. Okay? Right? And the dog is not dead. Okay? Until we know something about the premise. Okay, something if I bite the dog, okay, then this sentence becomes meaningful. But if not, then it's not. Okay? All right, so keep that in mind, because I often see, although this is very commonsensical, people make this mistake when they prove some formulas. Okay, so we are going to do some exercise on this. Let's see if I to do it here. Okay, good. Okay, so let's do that. I have very limited space here, so let's see if we can do. So the first sequence that we are going to prove is this. So given these two formulas, P and then not Q and R, can we derive not P and R? Okay, again, this P and R means some proposition or some sentence that is either true or false. Okay, all right, so maybe let's do this together. What should I write in the first line? P, because P is a premise. This is always safe to do. And another premise. Okay, I'm teaching you how to write a proof. Once you exercise this kind of thing a lot, then it will become easier for you to write a more mathematical proof in the mathematics. So like geometry and algebra. So many proof actually depends on this type of reasoning. Okay, so we are given this premise. What else that we can write? Not P? In where? Okay, well, the first thing is what is actually given and what is the goal to prove, right? Okay, so last line of the proof should be the conclusion, right? This is something that you have to write. I don't know what is n yet. Okay, once I fill in the middle, I will find it out. Okay, this is something that you can do. Now, of course, this last line, I know that it must be there, but I don't have the justification yet, right? I don't know how this comes out. So that's what we are going to do when we fill in the middle, okay? All right, but then let's actually think about it. What is the next step that we can do? Yes?
Not Q and not R.
Not Q and not R can be derived. Is that what we're trying to do next? Not sure how we can derive not Q. So maybe let's pause there. So you are saying that maybe we can derive not Q and not R here, right? How can we do this? Yeah, okay, so maybe the short answer is we don't know yet, right? Maybe this is true, we can derive, but if we want to write this line, I need a justification to be written here. And so far, maybe our deduction rules are not enough, I don't see how to do that yet. Okay, so maybe let's go back to what we have. Oops, okay, so let's just copy back this. Okay, what I want you to do is to look at the conclusion and try to think backward. If your goal is to prove a conjunction of not P and R, what is the sub-goals that you have to prove? So in order to prove this, okay, if you can establish these, then the last line can follow. What are these two formulas?
Can you get not P?
If you can get not P and also R. If we can derive these two formulas, then we are done. Okay. So since I don't know whether this is possible, let me just write not P and R here. Okay. But once we can derive this, I can simply say that this is conjunction introduction. So let's say this is n-1, n-2. From n-2 and n-1, right? So I wrote in blue because I don't know whether this is true or false yet. Okay, but if I happen to find out not P and R, then I'm done. Okay. So now your goal is to prove the line n-2 or line n-1. Okay. So we still have a gap between between 2 and n-2. So let's actually think about it. How can we derive the line n-2? How can we derive not P from the things that we already know to be true? So these two are known to be true. You can use it as much as you want. Okay? So how can we derive not P from these two lines above? Double negation introduction from line 1, right? So line 1 says P, so we can use double negation introduction rule. Then we can introduce the double negation there. So that's it. So let me just now turn it into red. So this is fine. From P, we can derive not P. That's it. Okay. Now our goal is to derive R. Again, what we can use is the first two lines. How can we derive R? Yes.
Can you do a double negation elimination
For
the parentheses?
line 2, right?
Yes.
Okay. So that's a good idea. Let's see. We can get rid of this because double negation is too much. Why do we need it? So we can eliminate double negation from line 2. So Q and R become true from not Q and R. So if we know not Q and R, then we can eliminate double negation, so we can derive Q and R. Fine. So that seems a bit simpler, but still our goal is to prove R, right? How do we go to R?
We use the
And the elimination, good. So we know Q and R, so we can derive either Q or R. For this particular problem, deriving Q does not help much, but deriving R actually finishes the proof. So from line 3, okay, it says Q and R. I can derive R. That's what line n-1 says. So I can do conjunction elimination, the version 2, for line 3. Okay? Now at this point, I closed all the gaps in the proof, which means that this is 4, 5, 6. So this is 4 and 5. Okay? Yes.
Does the order in which we make each of these statements matter? Like if I were to say line 3, not Q.
Sometimes matters and sometimes not. Yes. So there are some cases that the order does not matter. Okay. Order matters only when you have to use the fact that was already established. Otherwise, it does not matter. Okay. So let's look at the proof together. So once you write the proof from going from back to beginning or beginning to the back, you can now read from the beginning to the end. So here we assume P is true. Here we assume not Q and R is true. from this, of course, we can eliminate not, so we can derive Q and R. Now from P, we can derive not P, and from Q and R, we can derive R. Once we know these two, we can derive not P and R. We're done. That's the proof. Okay? Question about here? So if you look at the book, it just shows you the proof. But in order to see how you can derive this proof, there are some techniques here. Okay, so I'm trying to introduce you how to find which rules to apply. Okay, so there are some general principles behind it, and I'll probably summarize this later. But for now, the general rule is this: look at the goal. What formulas that you want to prove? That guides you which rules to use. And sometimes, if that you got stuck there, look at what you have already established. So try to derive something more from what you already have. And sometimes when you do that, you will see the gap between the conclusion or suppose that you want to establish between what you know is much closer. So you may be able to see better what rules to apply. Okay? Yes?
What is the meaning of the word and the two comma?
Oh, this is a name. I think we have this before. So this is just the name of the rule. So conjunction elimination, the second version of conjunction elimination. That's the name of this.
So it will always be not like
E means elimination. Okay, so the convention is we start with the symbol conjunction here, and then there are two things: whether we want to introduce the conjunction or eliminate the conjunction. Okay, and sometimes there are more indices to say which of these things. Okay, maybe that's a good point to think about it. Now, why is it called conjunction introduction? Because if you look at the new formulas, there is a new conjunction here. So conjunction is introduced when you apply this rule. Similarly, for the conjunction elimination, when you apply this rule, the conjunction in above the line disappears. So you eliminate conjunction. Okay? All right, and same for this. So the first one is double negation elimination. So between the first and the second line, okay, line above the formula, not 5 versus line below, which is 5, double negation was eliminated. Similarly, the second one introduces double negation. And if you look at, of course, implication elimination, you see implication was here, right? This implication is gone when you use these rules. Okay? Because I didn't actually introduce you the implication introduction rule because I need to introduce some concept there. Okay? So, but it will come. There is a version, implication introduction rule. Okay, so let's do one more exercises. So now I want to prove P implies Q implies R, derives R. Okay, so let's do this together. What shall we write?
P.
Yeah, no matter what you do, okay, write this. If you write at least this, you will get 1 point. Okay, if you don't write this, I cannot see. I can't see what to be given as a partial credit. Okay. Now, of course, one other thing that you can always write is the conclusion, right? So this R. Okay, so here we have to derive R, but R doesn't. The last formula doesn't contain any connectives, so it doesn't have as much, right? Because before, when we were looking at the conjunction, we can find out, well, in order to establish this, let's try to establish each of them, and we. But now we have just R, so we don't know much what to do, okay? But let's actually think in a forward way. So if you know first 3 formulas there, okay, maybe you can derive some new information just using the first 3. Okay? What can they be? Okay, let me write here is a premise. Yeah, we can derive Q. How? implication elimination on lines 1 and 2, right? Line 1 says P is true, line 2 says P implies Q is true, then together you can derive Q. That's implication elimination rule. So we derive this. So implication elimination for line 1 and 2. Good. What else?
Q implies R.
Q implies R. So which two lines that you have to use? One and three. If you look at one, this is a bit tricky because this P here and P here, and this is a complex formula. Q implies R. But the same rule applies. Whatever that is, this is a formula, right? No matter how complex it is, it's just phi implies psi, right? So this is the psi. So we derive psi, which is Q implies R, which is implication elimination for line 1 and 3. Are we together here? Okay. From line 1 and 2, you can derive Q. Line 1 and 3, you can derive Q implies R. Okay? All right. Now, we still have to go to R. So we try to use as much as we can, or maybe not. Yeah, maybe still something that we can do further. But how do we close the gap between phi and n? If that is, it's already there, right? So how can you derive n from the first 5 lines?
Implication elimination 4 and 5.
Yeah, if you look at 4 and 5, okay, 4 says Q is true, and 5 says Q implies R is true. Again, implication and elimination rule will say R is true. So we are done. Implication elimination for line 4 and 5 gives line 6. This is the proof. Let me actually go through the whole thing from the beginning to the end and take some questions. So what we established, we know P implies Q, P implies Q implies R is true. So these are true. Now if you look at first two, we can say Q is true. If you look at 1 and 3, we can derive Q implies R is true. Okay? Now if you look at 4 and 5, then you can derive R. So you're done. Okay, question.
So once you have once you have proved R, how would you relate those 4 different those 3 premises and then the conclusion? How would you relate those in a formula? If you ANDed all the premises together, would that be equivalent to just R?
No, so what we established is the whole necessary steps are already there, right? So how do we get R? Because 1, 2, 3 can, okay, so short answer is 1, 2, 3 can derive R, right? So I don't know maybe what exactly this question is about, but applying the rules, we can derive R, right? There's no question about it, right? So the meaning of this thing is basically, if you know 1, 2, 3, then R must be true. Okay, it's like a Lewis Carroll puzzle that we did before. If you believe 1, 2, 3, then you have to believe R is true.
Does that mean that they all imply R?
It's not necessarily implying.
What if you ANDed them all together? Would that then imply R?
There is a connection between them, but let me say that later. Okay? So you just want to be cautious. It's not called implied, it's called entailment. And here, in order to say implies, you have to talk about tautology, which is actually a few classes later. Okay? So for now, you don't have to worry about it. So all you need to do is, if I give you premises, if I give you a conclusion, how can you derive the conclusion from the premises using these rules that you're given? Okay? All right. All right, that's not too bad. Now, there are 2 probably most difficult rules for today. This is one. Implication introduction rule requires some idea here. So, the rule says this. You can derive this if you have a box where the start of the box is phi and the end of the box is phi. Now what this box means? This box is like a programming routine. Okay? So when you write a program, okay, some of the programming language allows you to nest functions. The functions can be inside another function and so on. So this box actually tells us the scope of this validity of this formula. Okay? So roughly speaking, when you say the open box and then phi, okay, this phi is only true inside the box. So you temporarily assume that phi is true. And then you try to derive some conclusions using phi and also some other formulas. Okay? Now, when we do this, okay, first, the phi is an assumption. So temporarily assume that phi is true. We don't know whether this is true or false. But let's just assume for the time being. Okay? Now, if you can somehow derive psi at the end, then now you can close the box and derive a new formula, phi implies psi. The question is, what formulas can you use inside the box? Inside the box, you can use any formulas that were established before, as long as that formula was not in a is not in a box that is inner than the current box. Okay, so here is actually a more visible thing. So I want to derive this, okay, and I also have some formula this, okay, and I also have formula H. Okay, so it's similar to the notion of global variable and local variable in programming language. So inside the current block, you can you can use the variables in the same block or the outer blocks, but you cannot use the block variables inside. Okay, so what that means is, so there are formula F, G, and H here. Okay, now if we want to derive, let's see, this psi, okay, you can use formula phi, and also you can use maybe other formula k, okay, because they are in the same box. However, you are not allowed to use F and G. Okay, because they are inside the box that is inner than the current box where psi is there. Okay. You can also use H because H is outside the current box. So outside the current box or outer boxes are fine. Okay, but the inner box you cannot access. Are we together? Okay.
So what are these F and K of these like
Formulas, any formulas. Okay. So phi, psi, F, G, H, K, they're all just formulas. Okay? Because in natural deduction, you see just a bunch of formulas written in line by line. All right, so this is the rule. Okay, now let's do the exercise. So there are two formulas. So from P and Q implies R, you can derive P implies Q implies R. So how can we derive this? Again, what do we do? Premises. So P and Q implies R. So that's the premises. And then I don't have other premise. I have only one. Okay. What can I do? Oh, I can write line N, right? Which is the conclusion. Okay. Now, if you look at the one on the right-hand side, okay, it's actually opposite direction. Okay, from P implies Q implies R, can we derive P and Q implies R? So let's also write this one. So here, the premise is actually the conclusion of the left one, right? And the line N is premise of the first one. Okay, so what that means is you can derive P implies Q implies R from P and Q implies R. And also you can derive P and Q implies R from P implies Q implies R. So you can go from one to the other and vice versa. That's right.
Is it always true that you can derive premises from the conclusion?
No, not at all. Okay, so let's look at the right one first because I feel like this is easier. Okay, from my old experience, looks like the right one is easier. Okay. All right. So, what can we do? If there are some connectives in the conclusion, try to use it. Okay. So we just saw the rules, which is if you have phi and psi, you can derive phi implies psi, right? Okay, this is the implication introduction rule that we just saw. Okay, now do the pattern match. In order to derive line n on the right hand side, what rule should we use? Do the pattern. This is phi, this is psi. What do we need? We need a box. Okay? And in the box, what can you fill in? Yeah, P and Q, phi becomes the first line of the box, and the last line is R. So this box is, say, temporarily assume that P and Q is true, and if we can derive R, then we are done. Okay? Now what we don't know yet is how can we get from line 2 to line n minus 1. We don't know in the middle, but we can fill it. Okay? Alright, so how do we derive R from line 1 and 2? Let's try to think as much as we can what formulas can be derived from line 1 and 2. Well, line 2 says P and Q, right? So why not we simply says P and Q? These are fine, right? What justifies to derive line 3 and 4? Conjunction, elimination from line 2. Okay? So we can get P and Q. Good. Now, we still have to go to R. We know up to 1, 2, 3, 4, they are all valid, right? 1, 2 are premises. So 1 is premise, and 2 is so-called assumption. Okay, because it's inside this box. I call it assumption. Okay, the difference between premise and assumption is premise is what you're given, assumption is what you're making. Okay, since we don't know if this is true or false, we just write a box. Okay? But our goal is to say that P and Q implies R is true outside the box. So we have to kind of eliminate the box. Alright. How can we get to R using line 1, 2, 3, 4?
Derive Q implies R.
Which two lines do we have to look at? 1 and 3. Look at 1 and 3. 3 says P is true. 1 says if P is true, then Q implies R is true. So you can derive Q implies R. So this is implication elimination from 3 and 1. Are we together? So we got Q implies R. Good. But we still have to derive R. What can we do? Same. So between which two lines? 4 and 5. From 4 and 5, we can derive R by implication elimination. Okay. So this becomes 6. This becomes 7. Okay. Okay, so once we write down this proof, let's do this together. The first line was premise. The second one, we don't know, but we try to assume P and Q, and somehow if we can derive R, then we can derive the last line. So we wanted to have this box, and then from P and Q we can derive P and Q separately. From P and P implies Q implies R, we can derive Q implies R, and from Q and Q implies R, we can derive R. Since we established the R from P and Q using implication introduction rule, okay, we can derive P and Q implies R. All of this is just a pattern match. Okay. So what we are not good at, what we humans are not good at, is to match the pattern. Okay. It requires some exercise. Once you exercise more and more, you will see these things. It's like algebra. Okay, you have to solve some equation. Okay, what do? You did a lot of exercises, right? How to move these formulas onto the left and right, and how to simplify. Okay, each of the steps is actually simple. There's a general pattern there, but sometimes you just stop, right? Because there is a pattern, but you don't know which pattern to use. Okay, so what I'm trying to do is try to help you which pattern is better to be used. Yes.
My other question is, how do you know what the assumption is going to be, what to assume?
Oh, that's a good question. You can use any assumption that you want. Okay, it is your assumption. Okay. The problem is you have to discharge the assumption at some point. So, for instance, I used P and Q there in line 2. I could have written any other assumption too, R or P implies R or whatever. Okay? But those other assumptions do not help me because I cannot use the implication introduction rule to derive the last line. Okay? So look at the last line. The last line 7 has P and Q implies R. The only assumption that I can think of at this point is P and Q to be assumed. And if we can derive R, then we can say P and Q implies R is true. Okay?
So what is it that says that you can't assume R? And then like if you just assume R is true, then does it
Then you cannot discharge the box. There is no way that you can do it.
and in order to discharge the box you have to use the outside formulas?
Yeah, the only rule that you know so far that can eliminate box is implication elimination rule. Okay, so as I said, you can introduce any box. Okay, that you have to be careful. So what you are saying is, well, say 1 P and Q implies R. Well, I will derive R here. Okay, maybe that's a good exercise to think about. So I have R, and then okay, then I will write R here. Huh? What is wrong with this thing? So R was inside the box, and I copied R outside the box. This is actually a very common mistake that I see from your submissions. There is no justification to doing that. Okay, you cannot. So R here in line 2 is only valid inside the box. It's not a universal truth, so you cannot take it out. Okay, you can only copy R inside another box. Maybe this is fine. If there's another, if you assumed R, and then you can assume another thing inside the box, but then you introduce another box, and now you have more boxes to clear up. Okay, that's actually difficult. So in general, you have to be very cautious about introducing the box. Okay? Yes.
So when we use an assumption, it doesn't make the proof not a proof anymore.
No, it is still a proof.
Like even though we don't know for sure that P and Q is true, the fact that
Yeah.
if P and Q is true, R
Good,
is true.
good point. So look at the line 7. I said P and Q implies R. Doesn't necessarily say P and Q is true. I said in the beginning, right? If I bite the dog will be dead. Doesn't mean that the dog, I beat the dog, right? Okay? So, then the point P and Q implies R is the go-to proof. Doesn't mean that P and Q is necessarily true. Okay? So if you assume P and Q is true, then I can derive R. That's what the box is about. Okay? But if you put the P and Q outside the box, suddenly that becomes wrong. Okay? All right. So it's actually quite interesting. No matter how many times that I say, I always see some solutions like this in homework. Okay? So try to avoid as much as you can. Okay? All right. Let's look at a bit more difficult one on the left. It's actually not very difficult, but I presume that you have to introduce one more box. So you have to introduce two boxes and here two boxes. That's what happens on the left side. So let's see what can we do. So line 1 and n are fixed. Okay, so that's the best formulas to write. What can we do for this? To derive line n, what is the thing that we can do? Again, yeah, this is implication format, right? So the way okay. So what I can do is I can introduce box, and inside the box P is true, and from this we derive Q implies R. So this is line 2 assumption. Assumption means that it's not necessarily true, but let's assume for this for now P is true. And somehow if we can derive Q implies R, then we can say P implies Q implies R is true. Okay, good. Okay, so now our goal is to prove Q implies R. Why? Because once we have this box to be filled in, the last line n can be derived from the whole box. So this is implication introduction from line 2 to n minus 1. Well, that's fine. You can watch the video and you can write down by yourself. So let me just write here. So P and Q implies R, and the last line is this one. Okay, and we just said in order to derive this, we can assume P is true and Q implies R is true. Okay, so implication introduction from 2 to n minus 1. Okay, now our goal is to prove n minus 1. So look at the subgoal, Q implies R. How can you prove it? Same principle, yes. So what? So here we need to also have another box, and the first line of the box is Q, last line is R, right? Once we have Q and R box ready, then we can derive line n minus 1. So this is another assumption. Okay, so at this point we have to close in the middle between line 3 and n minus 1, or n minus 2 actually, because we only need to derive R. So look at this. Line n was a bit complex formula, but now n minus 2 is much simpler formula. Line 1 was a bit complex, but now if you look at 3, it's actually a simple formula. Okay, so we actually got many simple formulas. So maybe there's a chance that we can close the gap between line 3 and n minus 2. What can we do? Line 1 and line 3? Line 1 and line 3? Line 2 and line 3. Right? Yes. So if we do line 2 and line 3, we can do P and Q. This is conjunction introduction to line 2 and 3. Okay? Now we still have to close the gap between line 4 and n minus 2. How can we do? Which two formulas, which two lines do we have to pay attention to? 1 and 4. Right? Are we together?
Yes.
Okay. So 1 and 4 together, implication elimination for 1 and 4. And this becomes 5, 6, 7. Oh, okay, now this is better than the previous one. I don't have to rewrite it again. All right. Okay, so let's go from the beginning. So I know P and Q implies R is a premise, that is known truth. Okay. Now I have to derive this. So P and Q implies R. So I know for this one, I don't know whether P is true, but let's assume P is true. And then if we can derive Q implies R, then we are done. Now, how do we derive Q implies R? Again, the same principle. If I assume Q, and if we can derive R, then we can derive Q implies R. So, how do we derive R from the fact that we established in line 1 to 3? We just introduce conjunction in line 4, okay? And then 1 and 4 derives R. We are done. Okay? Or if you want another explanation, here is the thing. So this is the premise. Let's assume temporarily P is true. And also let's assume temporarily Q is true. Then inside this box, I can assume P and Q is true. Am I right? Because I can access the current box and also outer box. So P and Q is true. If I know P and Q is true, I also know line 1, so I can derive R, which is this one. Since I assume Q and derive R, I can say that Q implies R is true. And also I assume P and derive Q implies R, I can say P implies Q implies R is true. We are done. Okay? Question?
So when you're writing your condition box on the bottom, do I still write assumption or do I leave that blank?
Yeah. The justification must be an assumption. Okay. And this is actually implication introduction from line 3 to 5. Okay, good. All right, so here is something. P implies P. How do we prove this? This difference here is there is no formulas as a premise, right? So we cannot write anything in the beginning. But the last thing is P implies P. How can we derive this? We assume, right? So we assume P. What? What is this? In fact, the proof is actually done. Believe it or not, this is line 2. Okay? And this is implication introduction on box 1. What? Actually, I said from phi to psi, we can derive phi implies psi, right? However, actually the first formula and last formula can be the same. And in fact, there can be only one formula. So this is actually valid application of implication introduction rule. Okay? Now what the rule says is if the first formula is phi and the last formula is psi, you can say first formula implies last formula. For this particular example, first and last formulas are the same. So you can say first formula P implies last formula. Now this may be a bit unintuitive, so some people actually use copy rules. So copy rules are not really essential rules in natural deduction, but the rule is actually simple, and people actually think this is more intuitive. So what copy rule is doing is, let's assume this, and you can copy the formulas that you can use. So P was already established, so we'll just copy this. Okay? Now then it becomes more closer to the rule pattern. So we say P implies P. Implication introduction for line 1 and 2. Okay? I don't mind which version that you use. Now for the copy rule, although, you have to be a bit careful. The same as what formulas you can use inside the box. Okay? So you can copy the formulas that are in the same box or in the outer box. Okay? But not in the inner box. Okay? The same rule applies here. Okay, that's about implication elimination introduction rule. Okay, so I'm going to skip this one, and I'll ask the TA to go over this in the dissertation section. Okay, let's actually do something here. What is wrong with this picture? So this is a part of the deduction rule. So you have A, and somewhere you have B and C, and D, and you can derive A plus D, and then you derive C. What is wrong with this?
Using C out of C.
C was inside the box, right? When you apply the conjunction elimination rule to derive C, okay, you cannot refer to the one inside the box, the inner box, right? So if you are saying that, oh, I know B and C is true, so I will get conjunction elimination from, let's say this is line N, this is wrong. Okay, if you want to apply the conjunction elimination or conjunction projection, that should be in the same box or maybe the upper boxes. Okay? Well, believe it or not, when you try to prove the sequence in the homework problems, you will see that you are stuck at some point, and you are tempted to do this. Because once you do that, things seem to be finished. So, okay. But it's actually wrong. Okay. Now, what about this? So you have x implies y implies c, and then you have a box. Okay. And the box has x conjunction with y, and then you eliminate x and y, so you get y implies c, and you get this and z. Okay. What is the mistake? Yes.
How do you do x and y? Why do you just do x and y?
Huh?
Like inside the box, the first one.
Oh, the box outside. Which line is wrong? Can you pinpoint which line is wrong? Line 3? Well, line 3 is okay because there's an assumption. As I said, you can assume anything. That's no problem. Yes.
Line 7?
1, 2, 3, 4, 5, 6, 7. 7 is wrong because
that's the last one.
yeah, 7 is wrong and also 1 is wrong. Okay, why 7 is wrong?
Use the inner y.
It should be, yeah, the formula is incorrect, right? What should have been derived here? X and y implies y or z. That has to be. Okay, so that's one mistake. What is the other mistake? From y implies z, you cannot derive z, right? So the formula y implies z doesn't say anything about y is true or z is true. Just an implication. Okay, good. Okay. Hmm?
For that last one, would you have made a new box and said like assume y to find z?
Maybe let's talk offline, okay? All right, so this one, okay. Again, I will leave this as an exercise in the presentation. Okay. It's also in the textbook, so if you're stuck, you can read it. Okay, so now let's move on to the disjunction rules. So there are two versions of disjunction, and of course, introducing the disjunction or discharging the disjunction. Introduction is actually easy. So if you know phi is true, then you can derive phi or psi is true. Or if you know psi is true, then you can derive phi or psi is true. Okay? So here I have two examples. James Harden won MVP in 2018. If you know this, you can derive phi or psi. Okay? It should be easier, right? Now, this is probably the most difficult rule in natural deduction. Okay? First, it uses three formulas about the line. So you have to use 3. Okay? Now, the 2 is actually the box. Okay? So this is yet another inference rule that allows you to discharge the box. Okay? So the box above the line disappears when you apply these rules. Okay? Now, the intuitive meaning is this. There are three things you can establish. So one is, first, I know that this routine gets input, and this input is either phi or psi. So phi means that the input to this program is always a non-negative input to this program is a non-negative integer. Psi is the input to the program is a negative integer. And these two together covers that input is all integers, right? Now, what you establish on the first box is if you assume that the input is a non-negative integer, then the output is negative integer. Okay? The second is if the input is a negative integer, you also get the negative integer as the output. From this, what can you conclude about this program? Assuming that the input is always integer, what can you conclude about the output? The output is always negative integer. That's what you can conclude, right? It does not actually matter whether the input was non-negative or negative, because in this box, when this was non-negative integer, we derive output to be the negative. And here, if the input was negative integer, we still derive negative integer as output. So no matter which case that we are in, we always get the negative integer as output. Okay? Are we together? So it's like a case statement in the programming language. Case 1, you get the negative integer as output. Case 2, you also get the negative integer output. And the case actually doesn't matter. No matter what case that you are in, you get the negative integer as output. Okay? Why this is difficult? Because of the three formulas that you have to find. But let's try a simple exercise. Okay? So P or Q derives Q or P. Okay? So for this class, as far as it's currently concerned, don't use other materials. Okay? So we know P or Q is of course same as Q or P. Okay? But what we want to justify is using the rules in the natural deduction. Okay? Don't do anything else when you do the program, when you do the homework. Okay? So only use natural deduction that you are given. Alright, so what can we do? So line 1, what is it? P or Q. Line N, Q or P. Now in general, this is actually difficult, but the hint here is to use the disjunction elimination rule. Okay? So this is the rule that we are going to say, and I'm going to give a hint. P is phi, and Q is psi. Okay? And this X symbol, I don't know how to pronounce, that is Q or P. Okay? So, what do we need to establish between line 1 and N?
Can you assume that P or Q implies some other function?
Let's actually look at the pattern. I just said P is phi and Q is psi. Okay? And this X is Q or P. Okay? So then what do I need? I need these two boxes. Okay? So let me actually write the boxes. Okay, I need two boxes. Okay? The first box I will assume P, and then the second box I will assume Q. Right? That's what I have here, right? I assume phi and psi in the another box. Case 1, assume phi. What is the thing that we want to derive? Q or P. Right? So this is line 2. And I don't know this line. But again, if I have this box is like this. Phi and X. This X is Q or P. So what I don't know yet at this point is between these two lines, and between these two lines, I don't know how to justify. At least for now. Okay. So what shall we fill in there? Are we together? I'm just writing the box here, just according to the pattern. So my phi is P, my psi is Q, my X is Q or P. So I just wrote this thing here. Instead of phi or psi, I use P or Q here. And for this box, I wrote P and Q or P. And for this box, I wrote Q and Q or P. And then from this, I can derive this X, which is Q or P. Okay, so the last line is disjunction elimination for line 1 and these two boxes. Okay, what I'm not sure is how to fill in the box, which is actually very simple to do. Okay, but what I did so far, I didn't need to do any thinking. I'm just applying the pattern. That's it. After that, I need to fill in the box. I may need to think. Luckily, this time is easy. How do we go from line 2 to the next line? Disjunction introduction. That's what we saw here. If we know this is true, then we can say this. Well, actually, it's second version. Okay. If you know psi is true, then phi or psi is true. So this is disjunction introduction from line 2. Okay, and this is assumption. This is premise. Line 5 is same disjunction introduction to line 4. Okay, so let's read from the beginning. Okay, so I know P or Q. There are two cases, P or Q. Case 1, if P is true, I can derive Q or P is true. Case 2, Q is true. If I assume case 2 assumption, I can derive Q or P is true. Which means that no matter which case that we are in, we can always derive Q or P. Are we together? Okay, good. All right, so since this is the most difficult rule, I'm going to repeat this again. Okay, so try to do exercise by yourself, and there are a few exercises for the disjunction elimination rule, and there are two more rules, and then we are done with the primitive rules. And after that, we have some derived rules, which can be, which are not the essential rules in the natural deduction, but can be useful like a macro in the programming language. So if you know those derived rules, the proof can be this simple. And by after that, you will be probably ready to do all problems in the homework. Question?
So when we have multiple boxes and we need to provide, like, we use the box for explanation, how would I say, like, I use this box versus
Yeah, so that's actually, I should write here instead of this. Since at that time I didn't know the box, the line number. So I should say disjunction elimination for line 1 and 2 to 3 and 4 to 5. This is a justification that I can write.
Okay.
Okay? Any other question? Okay, so today I introduced many rules, and again, this is not that easy to grasp at the first sight. You need a lot of exercises to do. So, so try to write down the proof as I show you today by your own writing. So don't look at the solution that I wrote, okay? But just try to understand the deduction rules and try to derive this by yourself. If you can do this, you'll have no trouble in the homework and the quiz and the test. But I often observe that students don't do this and just read the proof and seem to understand, but actually when they write the proof, they don't get it. Okay, so be cautious about it. So prepare your own solution notebook and write down all these things by yourself. That's actually the best way to prepare. All right, so let me open the Socrative now.